Okay, today linear algebra and electromagnetism. I'm just going to do a small recap on linear algebra, then I go to the new part. It isn't a lot because today is mostly electromagnetism and tasks, but that is all right as well. Okay, so let's go. How can we find the B coordinate? Yeah, okay, so what we had the last time is that we wanted to find the B coordinate for some given x. So we have a vector space V of some kind, right? And then we define, or we could say there's multiple ways. You could say that our basis defines the vector space, but it also, of course, it enforces a coordinate system. We're going to get more to that later, but it enforces a coordinate system on to V. So let's say it's just like B1 and B2, right? Just like that. And we need these spaces, right, to be fixed because there's a specified set of vectors that most efficient span V, right? And if we want to find the B coordinate, so a coordinate for our x with respect to the basis, that's pretty simple because x should, of course, be some kind of linear combination here of CB1 plus then CB2. And the tuning of that vector is, of course, C1 and C2, which is the coordinates with respect to the basis. So C1 and C2 are, of course, the coordinates. Okay, so let's look at an example. It's the example from last time here. So B1 is equal to 2, 1, right? And B2 is equal to minus 1 and 1. And then x is equal to 4 and 5. Just like that. And B, of course, is the basis. I don't need to write that. So find the coordinate vector of x. You could say relative to B, or find the coordinate vector of x with respect to the basis, right? Okay. So again, you can write the same thing in just another way. We could say 2, 1. I have this machine here, 2, 1, minus 1 and 1, right? And I need to run through these two dials here, C1 and C2. And then the output should be x, right? That is one way of saying it, right? So through this machine, which is my basis, if I have the correct dials, should give me 4 and 5, right? Is the same as we have here, right? So you just need to find C1 and C2. There's other way of saying that same thing also. I could state this guy as P of B, right? So this is a matrix, we could just call it PB. And then what I can do now is I could say the same thing that we have there is that P of B, and then this guy is, of course, the coordinates with respect to our basis. That is what we are looking for. And that should be equal to x, right? Which is on the right-hand side. Okay, now something special arises here. Remember, basis, they should be row reduced, or of course, if I row reduce basis, that should give me pivots. And if they give me pivots, of course, this matrix here should be invertible. So we can apply the invertible matrix theorem, which means there is a single solution here. And if it is, I can just apply the inverse of that matrix. So I have PB like that, I have X, and I have with respect to the basis. Now I multiply the same on this side, and then I have X like that, and this is of course just, what do you call that vector again? Oh my days, the unit matrix? I don't remember the name, it's alright. But that's just one in terms of matrix term. And you can see that one solution is also just running x through the inverse of our machine. That can we also do. That's a solution to our problem. So we could just augment that matrix there, right? And just do the inverse. So we could just do 1, 1, of course, row reduce. So we move this guy on the other side. And then when you have done that, instead of C1 and C2, you can run through 4 and 5 through that matrix, and the output would now be instead C1 and C2. Just like that. So that's also a very neat and nice way to view this. Okay, so that was very cool and good and great as well. You can also see that we have actually represented x in two different ways. You can see that this right here is actually the same as this right here. There's no difference from this, right? That's also very interesting, right? You can represent x as this transformation of x here, the coordinate with respect to the basis, through PB, right? And we actually call this matrix, I think is the coordinate system change, something like that. Matrix. I don't remember the exact word. Was it coordinate system? Let's see. I don't remember exactly. It isn't so. Change of coordinate matrix. Yeah. And that is what it does, because it changes from with respect to the basis to just x here, right? That is what it does. Okay. So that is very neat. Yes. And also this, you could see we could go back and forth here. So this has this also has a one-to-one relationship if you think of mapping. So going from x then to this, just a mapping here, is just a one-to-one relationship, right? Like this, which means that we have some kind of linear transformation, and that's just a one-to-one relationship, right? Okay, right, so we can now carry on this idea here very neatly, because now what we did actually, which was important, is that we enforce some kind of coordinate system on our vector space. So our basis, right, our basis B enforces some kind of coordinate system on our vector space. That's important. But the problem now is that that coordinate system may seem unfamiliar. So the next thing I would do, I would of course translate it to what we know, which is of course R of n of some kind. That is what I think is the conclusion. I don't know if that's correct, but that's how I think about it. So what we have then now is that actually that mapping we had, it's V with our basis, right? And we can actually map that into those coordinates with respect to the basis. That wasn't good drawing. That was nearly good. With respect to the basis, and this is in Rn. So we have x here, and if we run through the same thing with that respect to the basis, we actually just end up with a vector that's in Rn. That makes sense, because if you look at 4, 5 here is some kind of linear combination with, you see here, C1, and then you have something like, in this case, what did we have? We have 2, 1 and minus 1, 1. That's not something we are familiar with. We are familiar with the standard basis. But you see here, C1 and C2 themselves, they are just with respect to standard basis, right? I think that's the idea. So when you actually go from the space X, we actually move from the vector space V with our vector X that is defined by those coordinates with respect to the basis and the basis. If you just use the coordinates, we are in Rn. That is what's very neat, and I think that's the conclusion here. Okay, because that would make all sense if that was it, right? Okay, so it's actually a theorem here. So the coordinate mapping, that coordinate mapping that we have is a linear transformation and a one-to-one relationship. This guy right here, that is the theorem, right? So in the proof, we are not going to prove the one-to-one, but we can prove that it's a linear transformation. Remember, for a linear transformation, of course, we need the linear transformation. We need to have, of course, that we can add and that scaling property. Those are the two requirements, right? And we can try that. So in order to do that, we can of course. So let's say for let's say I picked some kind of vector u, right? And that vector u, let's see, how can I do that? Vector u is equal to some kind of c1, right? But now, and that doesn't quite make sense, right? I need c1. I'm not quite certain how I want to do this. Let's see. Okay, let's try. Just so we say u1 is just some vector in our vector space. So c1 and b1, right? And that's just up to cn and then bn. And then v is just, of course, d1, which is just b1 plus, then up to cn. No, c, you moron. d1, dn, and bn, right? So just two vectors in v. Okay. Now, of course, we have the coordinate space, right? So we can check. Now we have those two. So I could say, let's say what we did was, let's say we did u, and then we have, maybe we have u plus v, like that, and then we do it like this with respect to the basis. Okay, what do we have then? Let's see. Now we have to use our brains here. Remember, this is the same now as C1 plus, now, because these are going to be columns, plus, of course, B1, right? That's correct. Up to Cn plus Bn, right? These are, of course, just scalars. So what we can do is you can just move them. This is the same as saying C1, then up to Cn, and then, of course, plus B1, and then up to Bn. Just like that. And what is that? That's, of course, the same as saying U, then B, plus, of course, V, and B. So you see addition here is preserved. And now you can easily see if you follow the same argument. Let's say you have some R times U. Okay, what if you instead now did R U like that, and you do that with respect to the basis? That's of course just R times C1 all the way for R to Cn, right? You of course can move R outside, and you have the same column that we had earlier, and that is of course just equal to R, and we got R outside, which is what we want, and B there. So this is indeed a linear transformation. I think that is correct. That makes sense, all this. So here you see the argument I had, right? Same thing, U and V. Yeah, that is very sensible and nice, and this too, right? And we are not going to, that's an exercise to prove that it's indeed a one-to-one mapping. Here's the theorem. Yeah, vector space, the coordinate mapping is a one-to-one linear transformation for, yeah, I actually should have said it for the space, not for these two, but for the from. Oh, it's a linear transformation of this guy, but it's from, of course, that vector space to R. Yeah, that is even more precise. Okay, but it's fine. It's the general interpretation that matters. Okay, so now let's go to physics and its electromagnetism. We don't have too much time, so I'm just going to pick tasks that are more interesting. This is, yeah, this is not interesting. Not this either. This is also easy. Let's see. Is this one interesting? Electric dipole. Let's see. Okay, line charge, visualization, point charges. Okay, maybe we just do this. We just start at 2, 4 and just work our way downwards. Okay, an electric dipole consists of two particles. Particle 1 with charge Q at R1. Okay. So we have particle 1 at A, 0, 0, and particle 2 at minus A, 0, 0. Right. Okay. That's our dipole. So they're both at the x-axis, so I should flip the system to x, y, and z, just like that. And the first one, Q1, is at A. There we have Q1 and A. And the second one, minus Q, is at minus A, of course. Yeah. So R1 is the positive. Okay, make a sketch of the system. What is the direction of the electric field E for a point on the y-axis? What's the direction for a point on the y-axis? Okay, so this is our here. So if I choose some point on the y-axis, right? So let's say I chose this point here. What would happen is that this charge right here would push me like this, right? But this charge right here, that would pull me like that. And of course, those two will cancel. So what will end up is that just this component will matter, right? So it's just the electric field, E, right, is some kind of, let's say, constant, it doesn't matter, but it's in the minus x hat direction. That is what I intended to say, right? Okay, so if you go back here, make a sketch, what is the direction? And the answer is minus x hat, right? Okay, what are the two r vectors used in this argument, right? The r vectors appear in the expression. Yeah. So the two r vectors, right? The r vectors point to what's happening, or to where the, you could say, to where it applies. That's what the r vector does. So in this case, the r vector points here because it's applied there, and the r vector now points here because it's applied there, right? That should be pretty much correct, right? Because I could even, was it the question to write it? Yeah, I can of course just write them. So if I pick some Q, right, that means that R in itself is just 0, Y, and 0. R1 is of course the positive one, so that's 0, A, and 0, and R2 is just 0, minus, why did I think about y? It's the x-axis. Don't stress. A, 0, minus A, 0, and 0, just like that. That means that the relative vector 1, 2, 1 is just r, of course, and that minus r1, right? That's of course we just get minus A, right? So minus A, Y, and 0. And R2 then is of course just R minus R2, just like that. Now R again is 0, so we get minus minus, that's positive A. And then we just have Y and 0. So those are our two vectors, right? So the first one, minus A, right? And is that correct? Let's see. So R1, we go minus A, and then we go positive Y. The second one, we go A, and then we go positive Y. So that's indeed correct. Okay? Yeah, so that's correct, as you see. For a point charge, for a point in plane through x equal to A, parallel to the yz plane, that is AYZ. What are the two r vectors needed to find the electric field, right? So what we have is some kind of plane here, right? That is, of course, like this. I can just, to make it clear that it's, yeah, that was not too bad, like that, parallel to the z-axis and parallel to the y-axis. So the plane would go something like this. That's not too bad of a drawing, right? That was shit, but it's alright. There is a dot setting, but I'm too lazy to use it. But this is, of course, our plane here, right? Okay, so we want now to find any r on that plane. So what are the two r vectors that needed to find then? The electric field, let's see. So for a point in plane directly parallel to y, that is the point r is equal to a y set. What are the two r vectors needed? Of course, we need to point again, same thing again. We had now r was equal to a y z, but otherwise it's the same. So r now is just equal to a y z, and now r1 is just equal to, we just get 0, right? So I get y minus y, so y goes away. Otherwise it's minus a. It's 0, right? And it's minus z, just like that. Isn't that? No, r is first, and I am a moron. Yeah, what was the first one? I shouldn't be too quick, right? So r1 was a, so that one is 0. That one is 0, right? And then we have y and z. And then r2, the first one is a, y, and z. And the second one is minus a. So now we get a, and then we get minus a. So we get just 2a, y, and z, right? Can be a little bit quick. That's also sometimes nice. But that should be correct, of course. Let's see. Yeah, 2a, y, and z, and of course 0 there as well. Okay, final expression for the electric field, E, A, Y, and Z. So we just have 2 point charges. That means we can just sum them up, right? First, what we can do is just, by the superposition principle, we can just do them individually. So E1, right, of R is equal to the charge we had at the first, it was a positive q, divided by 4 pi epsilon 0, right? Then we have r1 and divided by r1 cubed, just like that. That is the same as q, 4 pi epsilon. That epsilon there was horrible, and I don't know what my pi looks like, but it's all right. And then we just have r1, and r1 was just 0, y, and z. So we have 0, y, and z. And then we have divided by, of course, y squared plus z squared. And then 3 over 2, right? Okay? And then E2 is just minus the whole thing because of q, right? And then what we have was 2a y z, and then divided by, now this gets a bit weird, but it's alright, so we have 4a squared plus y squared plus z squared, then 3 over 2. And all you have to do is just add them together. You just write those two expressions. So the electric field then is just E1 and plus E2. I'm not going to write them because I just repeat what I already written. And I'm too lazy to do that. Okay, so that should be very good. And you see this is all correct. And then the question is, what type of coordinate system would you use to take advantage of the symmetry of the problem? Provide an argument for your choice. Yes, okay. There's two immediate arguments. When you're alongside a line, right? Now we think this is true just on the y-axis, but if I kept my position here and just turned this around, this will be true anywhere. Like if I drew these two vectors the same way on this point here on the z-axis, that's the same. As long as I keep the same radius here all the way, which means that of course a cylinder here would make sense. This also makes sense if you look at down here, because this, it can just be a row, right? The same here, and that of course simplify our expression very much, right? So of course a cylindrical system would, right, would take advantage, right? Okay, yeah, and that is, yeah, around x, right? What is the electric field E expressed in this coordinate system in point R, X, Y, and Z? So now you just have to be a little bit creative, because now we have the core, we usually have it around Z, but now we have around X. So actually, our typical axis that will be X will be Y now. So we will use Y, or you could say, yeah, so Y is equal to now rho cosine of phi, right? So you can imagine that phi is here, right? So phi is some angle here, right? That's phi, okay? So you can imagine that our plane now is like this, right? With y, z, and then x like this, okay? Pretty easy. So y is just that, and that's of course in the y-hat direction. Then what you have is z as of y now, which is just of course rho, and then sine of phi, and then of course in the z-hat direction. Now x acts as z, which is just that x is equal to x times x hat, right? So I should have written here that these on the left side, of course, are vectors, but you get what I'm trying to say here. Okay, so that is the full idea here. And now, of course, rho is the same way. It's just y squared plus z squared, and you just take the root of that. That is what it is. Okay, yes. Okay, so now we have to set up the electric field. And all you have to do is just substitute. So you can just substitute for our expressions. So what you can do now is just directly translates. So the first one, right, y and z, you just get y cosine. So what you have is that you have rho cosine of phi y hat plus rho sine of phi z hat, right? But you see, that's just a row vector, right? We have the radius. It's like with x. We have now the vector for r, right? In this plane, of course. So what you actually have is q. You have 4 pi epsilon 0. And now this can be greatly reduced, because we just have, we still have 0 there. But here we have rho in the rho hat direction. Very neat. I should have actually written that as just that, but yeah, that seems a bit weird. No, that actually works. We can actually do that, because I have to substitute for that guy. But shouldn't I just write rho hat, or inside the coordinate there? That seems a bit silly, doesn't it? Right? I should just say here rho in the rho hat. We still have x, but that's 0. Let's keep that for now, and let me just use my brain for a second. Okay. And of course here, this one gets very neat, but this is just rho cubed. That's very awesome. Oh, is it? I feel like I should put, because I just replaced that guy, right? That's rho in the rho hat direction. What did I had that? I can write it like that, can't I? Y and Z. I like to do that instead. Let's see if we think rho cosine of phi and then y hat plus rho sine phi, and then we had z hat just like that. That is not in coordinate form, right? This is the coordinate form. Would I write r hat? No. I think that's correct. Next one is easy. So I'm just curious on this guy. Where are you? Okay, maybe we just move. I want to see that guy. Yeah, I just screw this. Oh shit, I forgot something. I forget this is a new R. My mistake. Oh my days. I forget also. I was too quick. Sometimes I just do that. But I was correct. I just forget that we don't have the same R. Of course, I can't use the same expression. R was a new expression. I was thinking about A. Yeah. So R is in X, Y, and Z. Let us do this again. Okay, so we had R was equal to X, Y, Z now. Because I used the last one, right? I used this with A. That's not the same. Oh, I could just... Yeah, we could just greatly simplify that. Because, let's go back. If that is the case... let's see. Okay, I should change that, right? That would be stupid. Yeah, let's do this properly instead of being too quick and doing stupid things, right? Okay. We need to create that again. Yeah, agree. And with the link, yeah, screw you. R is equal to X, Y, and Z now, which means that our R1 now is something different because we had A, that's just A. So it's just now, of course, X minus A, Y, and Z, right? And then R2 is equal to then, of course, we get X minus minus A. That's just X plus A, Y, and Z. And now we need to, of course, substitute. I was right. I was just too quick, right? When I'm doing this session sometimes, I just want to do more tasks and get finished earlier. So, yeah, instead of just doing this properly. Okay. That is all right. Yeah, then we can just write what we had. So we have Q, and Q was the positive one for the first one. Then we have 4 pi epsilon 0. And now in the first coordinate we have x plus a, right? No, I mean x minus a. We can say x minus a, and that's, of course, just in the x hat direction. Then we can use what we had. That was still correct. Rho hat. And then we divide, of course, by x minus a squared. And then we have plus rho, and then we have rho just squared, and then all of this is 3 over 2, just like that. That's correct. And the second one, so this was E1 now, and the second one, E2, of course they are vectors, is now minus Q 4 pi epsilon 0. Now instead we have x plus a in the x hat direction. We still have that same rho argument, right? And then below we have, yeah, it's just the same, x plus a squared plus now rho, and then 3 over 2. So that should be all right. And I, of course, forgot to change. But here you see, here it is. Okay, perfect. That is all right. So here you have, it should be entirely correct. X minus a, x hat, yes, rho. Yes, 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 it's entirely correct. Okay, pretty neat. Exercise 2.5, line charge. Okay. So, a rod of length L has charge Q. We place the rod along the x-axis with its center at the origin. Make a drawing of the system. What assumption would you need to make an approximate this as a line charge with, yeah. Okay, so we need 3 coordinates here. They already written this in 3 coordinates, so let's do this. It's alongside x, so I actually do the same thing again. I flip here. So x is on the right, y is on the top, and z is on the bottom. I'm gonna get back. Just give me some seconds here. And then you had some rod there, right? That's our rod. And of course, this place here, what was the length of this guy? It was L, so here is just L over 2. And here is minus L over 2. Okay. So here you see is the rod, right? Perfect. And then, what assumption would you need to make an approximate this as a line charge? Yeah, you need to assume that this is a continuous, that charge is uniformly distributed and continuous across all of this rod, right? So you can imagine that this is just particles that are uniformly distributed throughout, charged particles throughout the whole object, in this case just the length, right? Okay, so now we should find the density, so just the length. So the density, of course, of the length, you can just say L is just the total charge Q, and then of course just divided by L. Nothing more fancy than that. Okay, so just Q over L. Then a small piece of the rod X plus the axis length dx. What is the charge of this piece? So what we have for that piece is that we are at some x here, and then we are at some x plus dx there, right? So this part is dx, right? Okay, and dx, nothing more special than that, dx is of course just dl here. So we have not dl, what I'm trying, no, dx, what I'm saying, dq, it was the small charge, so dq, what was what I meant? So dq is of course just q over l, right? And then of course dx, like that. Okay, nothing more special than that. Yeah, we could use also the density here. That's actually what I did the last time, but it's the same. Okay, we want to calculate the electric field 0, y, 0 along the y-axis. What is the contribution from the field from piece dx at x expressed using the r vector? Write down an explicit expression for the r vector. Okay, so you see we have, of course, a rod here, and if we want to calculate what was it, the electric field on the y-axis, you could see that it's just in one direction, actually. Because again, this guy pushes there, but we also have a push there. So the push itself is just up, right? You can see that very clearly. So what is the contribution to the field of the piece dx at x expressed? So we just want one piece first. Write an explicit expression for the r vector. So we just have then dE then. That is what they're asking. So dE, right? dE is just, of course, that density, right? So rho L divided by 4 pi epsilon 0. And then we have our relative vector r, right? We have r cubed. That's also correct. And of course now, integrating over the line, we just have a small piece, and that's just dx, and we note that with that guy. Because we are integrating over x, right? We're not integrating over the position we have, which is just, of course, a y. So we have 4 pi epsilon 0. Then, of course, r is, of course, that rod, and that rod just someplace on that rod. So I just write 0, y, and 0, our position, minus someplace on that rod, and that's just r, x, I mean prime, and prime just notifies that this is indeed what we are integrating over. So that is, of course, just minus x prime. And then, of course, what we have is y and then 0. And then we have x prime squared plus y squared, and that's 3 over 2. Just like that. And that is, of course, just dE, and that should be correct. So the r vector is just minus, because again, where is the situation, right? We are measuring, let's say we had some point here, right? In order, if I'm someplace here, I have to go minus x prime and then y to get that right. So that should be pretty clear and correct. And the answer here, you see, is indeed correct, right? Okay. Write down the expression for electric field in terms of an integral. Explain what you integrate over. I already stated that. So now you just need to, this is just one piece, and now we need to collect all of those pieces over that rod, which means that the electric field is just collecting all of those small pieces from minus L over 2 to L over 2, rho L, that density, 4 pi epsilon 0, and now we just have the same thing. There's nothing special at prime, y, 0, x prime squared plus y squared, and then 3 over 2, and then of course I need dx, and just like that, prime. I forget the x there too, prime. Okay, pretty neat, very good. Yeah, that should be very much correct, as you see. That's good. Okay. Explain how we can use symmetry of the problem to simplify the calculation. What type of symmetry do we have in this problem? Use this symmetry to explain where you know the field if you calculate in the point 0, y, 0, right? And the same thing again. You could pretty much see here that I can rotate this point, you see? And I can rotate it anywhere. So if I placed just a circle here, I can rotate. And if I place a circle here, I can rotate around the x-axis. So again, it's a cylindrical coordinate. It doesn't matter. If I'm someplace out here between z and y, it still, the contribution is going to cancel out in this like this. And the only one that's going perpendicular, right? That is the one that matters to my point, right? Okay, so we can, of course, use that same property again. You can just explain, yeah, this is just, yeah, use this symmetry. Use this symmetry to explain where you know the field if you calculate a point. Where you know the field. Where you know the field? Doesn't make sense, but I think this is just explaining, so I've done that more than enough. Yeah, that's the same idea. Yeah, okay, right, that is all right. Now let's see, maybe we can finish 2.6 as well. That's fun. Okay, let's finish 2.6. Visualization of the field. The electric field in point R from point charge Q1 at position R1 is this guy right here. Yes, what is the electric? That's just inserting, we're not going to do that. B, the following function, E field Q returns the field. Fill in the remaining part of the program to make it work. Yeah, that's just, you write literally what's there. That's also easy, you're not going to do that. The field on a point lattice grid. Now I want to visualize the electric field found by a function such as this guy, right? We want to calculate the field points on a grid with a spacing A as shown in the figure. So what they want to do actually is create that mesh grid, but without using the function or method, to be more precise. What is the position R, Rij, for a point which is I units of length out along X and J? Yeah, so we have A, I and J, of course. That means that R, of course, I, comma J. If A is our step size, that's of course just A times I, comma A times J, just like that. Okay, that should be correct, yes. Now we need to visualize the field. So we want to create that grid, right? So our goal is to calculate the electric field. Now it's late. In an area that is in all points in the figure below, right? However, we would like to start enumeration from I equal to 0 and J equal to 0, right? We want to start fill out for I, right? That's what mesh grid does. You just place an axis right alongside y, and just place an axis alongside, or in opposite way. No, yeah, you place the y-axis along axis like we place every y-axis, right? And then you have to do the same for x, you do the same thing. So here we see the same idea. That's, of course, we want to start from I0, just move over here, and j equals 0. And we have, of course, two n plus 1 elements, because, of course, they are between these like pages, or what do you call it, fence, right? We are values between, right? If I have 10 fences, the distance between is going to be 9, right? Or the elements, I mean, not the distance, the elements between are 9, right? Okay, same with pages. So 2n plus 1 elements in each direction. Along the x-axis, we want to have n points along the negative x-axis, n points along the positive x-axis. Yeah, in total, n, and 2n plus 1 points. If you start the enumeration, right, what is the position Ri of a point, right? You can test this. So this in terms, right? If I want to go to the origin, I need to go first. I need to go positive n, and I need to go positive n. And we already have a, and we already have ai, right? So that means we had this guy, but now what we need to have, we need to compensate for n. So if I wanted to go, like I said, to the origin, I need to subtract n by ai, and then n minus aj, because a times j, I mean, because if we have, oh, maybe it's the opposite. Yeah, it's the opposite. What I'm doing? No, maybe it's n minus, is it a? Is it n minus a? Let's see again. Let's just think. Let's see. So I am at the bottom, right? What is the position R of some point? If I want to go up, I have to go up n, right? And if I want to just stay there, right, I have to write I is 0. Let's see. We have to be clever. If we start enumeration, I is equal to 0 and j is equal to 0, we should have then minus n, right? Okay. So you should have then, this should be the opposite, shouldn't it? But do I want that? Yeah. Shouldn't it be ai minus n, right? Because if I is equal to 0, we get minus n. And a j minus n. Now I'm just uncertain if we should use some parentheses. The step is I. That's the step. The step length is a. So what I could have is, what did I say? The step length was a. I could have I, that didn't make sense. I minus n. Right. Yeah. I could have a minus. Let's just try and think. Okay. So if I had now n steps, that would be n times a. That's not correct. No, that's not correct. Yes, I knew something here wasn't correct. Either I or a have to go outside. It's of course a. It's I minus n, isn't it? If I is equal to 0, we get a times minus n. Is that correct? We get n steps and a distance. Yeah. That should be correct, shouldn't it? Right? Isn't that good? Yeah. And j minus n instead. Because if, let's say, okay, let's try again. Now brain is stupid, but it's all right. Okay. So if I is equal to n, that's 0. if j is equal to n, that's 0. If they go to n, we should be at 2n. I think that's correct. We are either very close or we are stupid. I minus n. Yeah, that's entirely correct. Yes. Good. Great. In order to visualize the field, Python does this and that. Yeah, we need to, of course, loop out. That's pretty easy. We're not going to. You just need to fill out for those positions. It's not hard at all. Okay, no, we're not going to do that. And here is the improved code. Yeah, it's just mesh grids. It creates and does essentially the same thing. But this programming part is pretty easy, so we're just going to skip that. Okay, but now my time's up. I have to go to bed. So tomorrow is astrophysics. That's going to be nice, but I'll see you tomorrow.